Good day, everyone. You are welcome to today's lesson. It is a continuation of the previous class we had. In the previous class, we talked about the periodic table, and we said that periodic table has it has a vertical column and it has a horizontal row. The vertical columns are called the groups, whereas the horizontal rows are called the periods. And the groups are divided into three: group 1, group 2, group 3, and so on till group 8. And then the periods are divided into 7 groups: period 1, period 2, period 3, up to 7. Now, we went ahead to say that the group 1 elements are called alkali metals, whereas the group 2 elements are called alkaline earth metals. Also, we also said that the group 7 elements are called halogens, and then the group 8 elements are called the noble gases or inert gases or rare gases. So the topic for today's lesson is the electronic configuration of the first 20 elements, Shell's energy levels. The electrons in an atom are in continuous and constant motion round the nucleus in shells, which are represented by capital letters K, L, N, and so on. In fact, it continues up to M, N, L, up to 8 shells. The shell nearest to the nucleus, or the innermost shell, is the K shell. It is followed by the L shell, then the M shell, and N shell. What we are saying is that at the nucleus of the atom, we have shells surrounding the nucleus. We have about 7 shells: K shell, L shell, M shell, N shell, O shell, P shell, and L shell. But the first shell that is closest to the nucleus of the atom is the K shell. Now, each shell is at energy level represented by the principal quantum number N. The principal quantum number is being represented by N. There are other quantum numbers, but the one we are going to use for today's lesson is the N quantum number. The K shell is in the first energy level, where N is equal to 1. It has the lowest energy and hence the most stable shell. The reason why it has the lowest energy is because it is the first shell and is very close to the nucleus. And because it is the first shell, it is being represented by 1. The second shell, which is the L shell, is represented by N equal to 2. And so the M shell is in the third energy level, where N is equal to 3, while N shell is in the fourth energy level, where N is equal to 4. The higher the principal quantum number, the higher the energy level, and the farther away the shell from the nucleus. What we are saying here is this: that the first shell that is closest to the nucleus of the atom has the lowest energy, and its principal quantum number is N, is 1. Then the second shell, K, is the next shell after K shell, and its principal quantum number is 2. It follows like that to L shell, M shell, and so on and so forth. Then the higher the quantum number, then the higher the energy level. And on the other way around, the lower the energy level, the lower the quantum number. Or you can say the lower the quantum number, the lower the energy level. Usually, the maximum number of electrons that a shell or energy level can accommodate is limited by the formula 2n raised to power 2. Hence, the K shell, where n is equal to 1, can accommodate a maximum of 2 electrons, while that of the L shell n equal to 2 is a maximum of 8 electrons. M shell N can also accommodate only 8 electrons instead of 18 by calculations. So it has a general formula for calculating. There is a general formula for calculating the highest number of electrons each shell can contain. The formula is 2n raised to the power 2, where n represents the number of shells. So for the K shell, where n is equal to 1, when you substitute 1 for n here, you will have 1 raised to the power 2, which is equal to 1. 1 times 2 is 2. You will see that the K shell will have a maximum number of 2 electrons. But for the second shell, L shell, whose number is equal to 2, when you substitute 2 for n in this formula, you will see that you have 4 times 2, and it will give you 8. Therefore, the maximum number of electrons the K shell can accommodate in each shell is 8 electrons. That can be calculated from this formula. Now, I want everybody to look at the table on the board. The table below shows the shell electronic configuration of the first 20 elements. The first column contains symbols of elements. Then this column is atomic number, and the last column there is the shell electronic configuration. For the first element here, we have hydrogen. Its atomic number is 1, and its electronic configuration is 1s1. The 1 here shows the quantum number, and then the s there shows that it is s orbital. So the second element there, helium, it has atomic number of 2, and its electronic configuration is 1s2. We have the third one, lithium. It has atomic number of 3, and its configuration is 1s2, 2s1. The fourth one is beryllium, 4, 1s2, 2s2. Boron, 5, 1s2, 2s2, 2p1. Carbon, 6, 1s2, 2s2, and 2p2. Oxygen, 8, 1s2, 2s2, 2p6. Fluorine, 9, 1s2, 2s2, 2p5. Neon, 10, 1s2, 2s2, 2p6. Sodium, 11, 1s2, 2s2, 2p6, 3s1. When you notice here, you can see that for sodium, we have a third shell there, 3s1. It shows that sodium has 3 shells. For the first shell, it has a maximum of 2. Second shell, it has a maximum of 8 electrons. So 2s2 and 2p6 are the electrons in the second shell, whereas the 3s1 is the third shell, which contains 1 electron. So 11, which is the atomic number of sodium, has 281. 2 electrons in the first shell, 8 electrons in the second shell, and 1 electron in the third shell. Now magnesium, as we go on now, you see that the third shell, which is 3s2, has 2 electrons. And after magnesium, we now enter aluminium, where we have the fourth shell. So we have magnesium, 12, 1s2, 2s2, 2p6, 3s2. Aluminium, 13, 1s2, 2s2, 2p6, 3s2, 3p1. Silicon, 14, 1s2, 2s2, 2p6, 3s2, 3p2. Do you understand? Now for phosphorus, 15, 1s2, 2s2, 2p6, 3s2, 3p3. Sulfur, 16, 1s2, 2s2, 2p6, 3s2, 3p4. Are you following? Chlorine 17, 1s2, 2s2, 2p6, 3s2, 3p5. Argon 18, 1s2, 2s2, 2p6, 3s2, 3p6. Potassium 19, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Then the 20th element, which is calcium, 20, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. So the table has shown us the electronic configuration of the first 20 elements. We can see that the last element there is calcium, and it has 20 as its atomic number. Blocks of elements in the periodic table. Elements in the periodic table are in blocks based on the type of orbitals housing their valence electrons. There are 5 blocks of elements, namely S block elements, P block elements, noble gas elements, and D block elements, as well as F block elements. Now, the S block elements are those elements that are in group 1, P elements group 2, and group 3 elements. Then the D block elements are elements that are in between group 2 and group 3 elements, and we call them transition elements. Then the last block there is the F block elements, which comprises the lanthanides and the actinides. So in summary, the blocks that are found in the periodic table are S block elements, P block elements, noble gases, D block elements, and 5 blocks. So there are 5 blocks in the periodic table. S block elements. The S block elements are those elements in which valence electrons are in the S orbitals. They have outermost shell configuration of ns1 or ns2. They are in groups 1 and 2, and they are all metals. For example, lithium, magnesium. There are other elements that are in group 1 and group 2. The calcium is also in group 2 elements. Sodium is in group 1, and so many other metals that are in group 1. Then the P block elements. The P block elements are those elements in which the valence electrons partially fill the p orbital. They have outermost structure from ns2, np1 to ns2 and np5. They are in groups 3, 4, 5, 6, and 7 respectively. Examples are boron, carbon, nitrogen, chlorine, and sulfur respectively. Then the noble gas elements. These are those elements with outermost shell configuration of ns2, np6. That is, their highest occupied electronic energy level are completely filled with electrons. They have duplet or octet electronic configuration or structures. Examples of the noble gas elements are helium, argon, and neon. Now, the noble gas elements are otherwise called inactive gases. The reason why they are inactive is because they have a complete electronic configuration of either octet structure or duplex structure. What it means is that the that the last electronic shell contains the maximum number of electrons it's supposed to contain. For a duplet structure, where we have helium, helium has 2 as its atomic number, and it has only 1 shell. And remember, I told you that the maximum number of electrons the K shell can contain is 2. So if helium that has 1 shell has 2 electrons, that means it has contained the maximum of electrons it can contain for that particular shell, which is the K shell. So it cannot accommodate more than 2 electrons. In other words, it has its complete octet structure. So because it has 2 electrons as its maximum number of electrons, we say it has a duplet structure. So because it has duplet structure, it cannot react. Remember that the essence of reaction is to either accept electron or donate electron in order to attain octet structure. That is combination. The essence of combination or reaction is for 2 atoms to exchange electrons, either donating electron or accepting electron from each other in order to attain octet structure. Therefore, if an atom on its own has a complete octet structure or duplet structure, there is no need for it to donate electron again or accept electron in order to attain stable electronic configuration. So that is why noble gases do not react, simply because they have a complete electronic configuration in the form of either duplet structure or octet structure. I hope you are following. Now the next block we have there is the D block elements. The D block elements. These are elements in which the outermost electrons are in the D orbitals. They are all metals. Like I said earlier on, the D block elements are called transition metals. They fall in between group 2 and group 3 of the periodic table. Example of the D block element is scandium. Scandium. Another example is platinum, manganese, lead, arsenic. All these are examples of transition metal, which is the D block element. Now, in this configuration, we used AR squared bracket to shorten the electronic configuration because argon, as we know, is 10. So it has to be, instead of us to start writing from 1s2, 2s2, we just put it in short form, AL. AR means argon. So this is the continuation. So the D block elements are simply the transition metals. Now the last one there is F block elements. They have their outer shell electrons in the F orbitals. They are called rare earth elements. For these elements, 3 energy levels are partially filled. Now the transition metals. Transition elements are those elements that fall in between group 2 and group 3 in the periodic table. I have said it before that these elements that fall between group 2 and group 3 elements are called transition elements. I hope you are following. Good. They are called D block elements. There are 3 rows of transition elements in the periodic table. What I mean by that is that in between those elements that fall between group 2 and group 3, they are called transition elements. There are many of them, which comprises 3 rows. We have the first transition series, second transition series, that is second row, and the third row is the third transition series. Then the 10 elements from scandium to zinc in the 4th period form the first row series. They correspond to the filling of the 5 orbitals in the 3D subshell. Inner transition metals. An inner transition metal is one of a group of chemical elements on the periodic table. Periodic what? Table. They are normally shown in two rows below all the other elements. They include 57 to 71, that is the lanthanides. What did I say? Lanthanides. And the 89th element to 103 elements are called actinides. Everybody say actinides. Good. The lanthanides are very similar, and the actinides are all radioactive. Are all what? Radioactive. They are called radioactive because they can decay. And radioactive elements are very deadly. In some cases, inner transition metals are quite malleable and ductile. What do you mean by something being malleable is if its ability to produce sound. For example, the ring you use, the bell you use in the schools, where you ring a bell to indicate the time for break. The time for break, you go and ring, produce sound. That is malleability. The second one, the ductility, means metals that can be transformed into wire. For example, the copper wire you use at home, the copper wire you use in wiring houses is a metal, but it can be ductile. That means it can be transformed into wire. Many lanthanides, such as lutetium, are used in the lighting industry. Actinides do not occur in nature and are highly unstable.